Welcome dear students once again into the class of mathematics, and today we will discuss two very important theorems from the chapter of sequences and series. These are Cauchy's first theorem on limits and Cauchy's second theorem on limits. So let us start with Cauchy's first theorem on limits. Cauchy's first theorem on limits says that if an is a real sequence such that limit of an as n approaches infinity is equal to L, that means the sequence an converges to L. Then limit of n approaches infinity, a1 plus a2 plus a3 plus and so on an divided by L, that means the average of n terms, first n terms, this also has a limit equal to L when n approaches infinity, or in the other words you can say that the sequence a1 plus a2 plus and so on an divided by n also converges to L. So this is the statement of the Cauchy's first theorem on limits. If limit of an is L, that means if an converges to L, then a1 plus a2 plus and so on an divided by n also converges to L. So let us move on to the proof now. This was the statement, and now we are moving towards the proof of Cauchy's first theorem on limits. So let us see how to prove it. We are given that limit an as n approaches infinity is equal to L. This is given to us. Now define some sequence Zn as an minus L. Define this new sequence and take limit on both sides as n approaches infinity. So that means limit of Zn as n approaches infinity is the same as limit of an as n approaches infinity minus L, as L is a constant. Now what is this limit? Limit of an as n approaches infinity, this is given to be equal to L. So this is equal to L minus L is equal to 0. Or you can say this new sequence Zn, this converges to 0. Saying that the limit of Zn as n approaches infinity is equal to 0, or saying that the sequence Zn converges to 0 is one and the same thing. Now, your sequence Zn converges to 0. And what is the definition of convergence? Now we will apply. Since the sequence Zn converges to 0, therefore, for given epsilon greater than 0, however small, it is a positive number, however small, there exists some natural number m definitely belonging to the set of natural numbers, as m is a natural number. There exists a natural number m such that mod of Zn minus 0 is less than epsilon by 2 for every n greater than or equal to m. Whenever your n is greater than or equal to m, this mod of Zn minus 0 is less than epsilon. Or you can simply say that mod of Zn is less than epsilon by 2, because Zn minus 0 is same as Zn. So mod of Zn is less than epsilon by 2 for every n greater than or equal to m. Also Zn converges to 0. That means this sequence Zn is a convergent sequence, and we know that every convergent sequence is bounded. So that means Zn is also bounded. So this means the sequence Zn is a bounded sequence. And since Zn is a bounded sequence, there must exist some real number k such that every term of the sequence, its mod, its absolute value will be less than or equal to k, or you can say is less than k. So therefore there exists some real number k such that your mod of Zn is less than k for every n. This is true for every n. Earlier it was for every n greater than or equal to m, and now it is for every n. Now we will move on to the main thing. This is your Zn, and now we will talk about Z1 plus Z2 plus Z3 plus and so on up to Zn divided by n. Now note that mod of Z1 plus Z2 plus Z3 plus Zn divided by n. We know that mod of A plus B is less than or equal to mod of A plus mod of B, and this n is a positive number because it is a natural number, so it can be taken out from the absolute value, or you can say from the mod. So you can say that this is less than or equal to 1 by n times mod of Z1 plus mod of Z2 plus and so on. Here you will say plus mod of Zn. As our n is greater than or equal to m, definitely in between you will have somewhere Zm, so you will have here Zm, and then you will have Zm plus 1 plus and so on. This will be also in mod of Zm plus 1 and so on. Now we apply these two, this one and this one. Whenever your n is greater than or equal to m, that means I am talking about these Zm plus 1, Zn plus 2, Zn plus 3 and so on up to Zn. Whenever your n is greater than or equal to m, your mod Zn will be less than epsilon by 2. So this will be less than epsilon by 2, this will be less than epsilon by 2, this will be less than epsilon by 2, this will also be less than epsilon by 2. And for the rest of the terms, that means mod of Z1, mod of Z2 and mod of Zm, we will apply the second. That means mod of Zn is less than k. So this is less than k, this is less than k, this is also less than k. Now how many times you are going to get k? You are going to get less than k here, less than k here, less than k here, and these are m terms, so you will get m times k, and 1 upon n is also there, so you will get is less than m k by n. I am repeating why it is so, because this mod Z1 is less than k, this mod Z2 is also less than k, this mod Zm is also less than k, because Zn is always mod Zn is less than k for every n. I am just using up to m. So this is less than k, this is less than k, this is less than k, so you will get m times k, and there is 1 by n outside, so you will get mk by n. And now for the rest of the terms, let us see what is happening here. This is Zm plus 1, so that means greater than m. So whenever your n is greater than or equal to m, your Zn mod is less than epsilon by 2, so this is less than epsilon by 2. This is also less than epsilon by 2. This is also less than epsilon by 2. This is also less than epsilon by 2. And how many terms are here? If you count right from the starting to this, the number of terms is n. But m terms we have left. We here from Z1 to Zm, these are m terms, and total number of terms are n. So leaving these m terms, how many terms are left here? N minus m. So n minus m times epsilon by 2. Epsilon by 2 here, epsilon by 2 here, epsilon by 2 here, and n minus m times. And 1 upon n is also there. So it is n minus m upon n times epsilon by 2. Now, let us see what will happen now. This is from the last result what we have obtained here. This result I am talking about. I am going to write this result once again here. Mod of Z1 plus Z2 plus Z3 plus and so on, mod of Zn divided by n is less than mk by n plus n minus m by n times epsilon by 2. This. Now this n minus m upon n, I can write it as 1 minus m by n. I can write it as 1 minus m by n. M by n is a positive number, positive term, not number, it is a positive term, and 1 minus something positive is definitely going to be less than 1. So this bracket is less than 1. So I am going to write is less than mk by n plus this term is less than 1 into epsilon by 2. I am using here the inequality. Less than. So less than, this is less than 1. Rest of the terms are same. So you are going to get mk by n plus epsilon by 2. Now, once again, look into the first term on the right hand side. First term on the right hand side, that means mk by n. It is also a sequence. This mk by n is also a sequence because m is fixed, k is fixed, only n is a variable. So this is a sequence which converges to 0. Why? Because limit of mk by n as n approaches infinity is equal to 0. This is a constant number and n approaches infinity will give you the result as 0. So this sequence converges to 0. And since this sequence converges to 0, once again applying the definition of convergence for given epsilon greater than 0, however small, there exists some m1 belonging to n such that mod of this mk minus n, mk by n, minus 0 is less than epsilon by 2 for every n greater than or equal to m1. This result is true for every n greater than or equal to m1, and this result is true for every n greater than or equal to m. So if you take some m2, which is maximum of these two, m and m1, then both these inequality will be true. So take m2 to be maximum of m and m1. Oh, what will happen if m2 is maximum of these two? Then your mod of z1 plus z2 plus z3 plus and so on zn divided by n mod is less than mk by n plus epsilon by 2 for every n greater than or equal to m2, and this result, this is your mk by n minus 0 mod. M is positive, k is positive, n is a natural number, so it is also positive. So you can write it as mk by n is less than epsilon by 2 for every n greater than or equal to m2. And apply this result over here. Mk by n is less than epsilon by 2 for every n greater than or equal to m2. And here you are having mk by n. So this mk by n, since n is greater than or equal to m2, this mk by n is also less than epsilon by 2. So you can now write this result as z1 plus z2 plus z3 plus and so on zn divided by n mod is, or you can say minus 0 mod is less than epsilon for every n greater than or equal to m2. That means for given epsilon there exists some natural number m2 such that this nth term of a particular sequence minus 0 is less than epsilon for every n greater than or equal to m2, and by definition of convergence it reveals that this sequence converges to 0, or you can say the limit of this term is equal to 0. So this means limit of z1 plus z2 plus and so on zn divided by n is equal to 0. Now the last step, in the last step you substitute the value of each of these zi's. What is your z1? Your z1 is a1 minus l, as we have defined in the starting. Your z2 is a2 minus l. Your zn is an minus l. So substituting the values of z1, z2 and zn, you will get limit n approaches infinity, a1 minus l plus a2 minus l plus a3 minus l plus and so on an minus l divided by n. This limit is coming out to be equal to 0. So what you are going to get now, limit of n approaches infinity, this is your a1 plus this is your a2 plus this is your a3 plus and so on plus an n minus, this is minus L, this is minus L, this is minus L, this is minus L. How many times? N times. So n times L means NL divided by n is equal to 0. Now consider this as one term, this as the second term, and separate them. So you will get limit of n approaches infinity, a1 plus a2 plus a3 plus and so on an divided by n minus nl by n. So n will be cancelled out. You will be left with minus L is equal to 0, and taking this minus L to the other side, you will get this limit is equal to L, and that is what the result of Cauchy's first theorem on limits says. So this is how to prove Cauchy's first theorem on limits. In the second video, in the next video, we will prove Cauchy's second theorem on limits. Till then, thank you once again.